Numerical, chapter 21, numerics for ODE and PDE. We'll start with the ODE today, and maybe we'll even go to the PDE as well. All right? So what are the ordered differential equation we are trying to solve? Method for first order ODE first. All right? So this would be a first order ODE. All right? dy1 equal 5x plus y2 and dy2x equal 7 sine x plus y1. See, those are simultaneous ordered differential equation. I mean, you cannot solve this by itself. You have to solve the two of them together. You have to solve for y1 and y2 together. If this was just y1 and y1, solve it by itself. But when they are coupled like this, you have to solve them together. For example, this one, d7y1 dx7 equal 5 sine x e to the power x. This, you solve this by itself and get, what do you get when you solve this? I mean, you get an equation between y1 and x, right? You get y1 and x. So y1 is 7 sine x, or y1 is e to the power x divided by cosine x, or whatever. Numerically, we don't get the relation. But we get the second best thing. We get actually the values at different x. Why did you want the equation to start with? You wanted the equation so that you can plot it, or you have the table, you know, just like what we did in that homework. You plotted as function of x and t. So if I give you the Excel table, it would be as good as the actual equation, right? So rather than in that homework, rather than telling you the solution is cosine times sine, if I give you that table, it will be as useful for you as the equation itself. So that's what the numerical methods will do. We will never have the equation, and most of the time those equations are really long and very confusing to use and have a lot of sine term and cosine terms and coefficients. Numeric methods will basically just give you the values. When x was this, what was the y? Or in case of partial differential equation, when x was this and t was this, what is the function? All right? And if you say, but you know, the equation can give me the solution at any x, and if you give me a table, you are just limiting me to the value that you are giving me. You know, it's like 0.1 and 0.2 and 0.3. What if I want 0.15? Well, when you're doing it numerically, you have a choice on that step. So that step, we are moving the variable with x. You can make it as small and as fine as you want. All right? So if you're interested in solution not every 0.5, but every 0.1, go for it. So make basically the step 0.1, 0.2, 0.3, and the solution will come from those numerical methods as basically 0.1 and 0.2 and 0.3. Right? So refinement of the solution, that's not an issue. Okay? It's accuracy. That is the problem. So the solution may not be accurate compared to the analytical solution. So the analytical solution is the exact solution. The numerical solution is an approximated solution, and we will see why in a second. Why it's not the exact solution, it's approximation. But that approximation will be very, very good, or will be very, very close to the solution, the exact solution, if the h, the step that we are taking in case of ordered differential equation, is very small. So if you make h very small, this will allow you to basically get the solution correctly. All right? Of course, that means a lot of time steps. So, for example, let's look at the first homework problem. So here is an ordered differential equation. This y prime mean, what does this mean? Yeah, dy by dx is 1 minus 1 over x minus 1, that's 1 over x multiplied by y. Okay? And he's giving us y of 1 when x was 1, y was 1, and he wants y of 2. Right? And he's giving you h equal 0.1. That's the step that we are going to get the solution with. If you use a bigger h, so that you want to get the solution immediately, you know, you want to make an h equal 1, so that you go from y1 to y2. The solution may not be really that accurate. If you make h small, the step small, you will see right now why the solution will get more and more accurate. So in this problem, I'm giving you the h. In another problem over here, for example, here's another differential equation. I didn't say anything about the step. The step that we are integrating with, I didn't say how much. It's up to you to decide. Right? What I said that I want the solution to be accurate within 4s. So this will involve basically trying different h, trying different steps, and realizing that after we make it small enough, now the solution doesn't change. Its first 4 digit does not change. You are done. But if you make very big h, you will find out that the solution basically is not, you don't always get the same number. What I'm saying is that, for example, you try h.5, and you get the solution 3.000. You try h.4, and you get the solution as 2.975. That's not the same as 3. Which one is correct? Probably the one with a smaller h. You try even smaller h, and the solution now start to kind of converge, doesn't change that much, and then that's when you know that now my solution does not really depend on my h. I managed to make my h small enough that my solution doesn't change. Alright? So that's basically the drawback of numerical method, that their accuracy depend on the step that you are using. Alright? The convenience, you will see that basically that it's very easy to integrate something like this numerically, which may be really hard analytically. Alright? So let's start with just one equation. Forget about the system. We'll do system of ordered differential equation at the end. But now let's just have one equation. Okay? dy by dx equal a general function of x and y. Could be any x and y. 5y plus sine x, 5y times sine x, 5y over sine x. Okay? And those initial value problem, they call initial value problem because you need to give me at x naught what is y naught. You need a starting point. And then I will integrate as function of x until I give you a table between y and x, or eventually I will give you the value at the end. Huh? Like for example, in that homework, this is the compressible flow of air in a pipe, insulated pipe with friction. So I'm giving you the Mach number at the beginning of the pipe. So imagine air is going at Mach 0.6, that's pretty fast. Okay? That's faster than the wind tunnel we have over in the main hole. You cannot go more than 0.3. So it's 0.6, and he's going into a pipe with friction. He's giving you the F and the gamma. Driving the ordered differential equation for a system like this, that's not this course. It's compressible flow. You will get this when you're taking compressible flow, 3293, and the equation will be this. That's ordered differential equation. So he's giving you the initial value, and he's asking for the value at the end. He would like to find at the end of the pipe what will happen to the Mach number. What do you think? You think the flow will speed up or slow down? Appendix B was for isentropic flow. This is duct with friction. That's appendix F. So back again to the question, what do you think will happen? Mach 0.6 at the beginning, duct with friction. Actually, he will speed up. Wow, amazing. You have to take compressible flow to get it.
Wait, we haven't covered that yet.
Yeah. He will speed up. And so now, see, this is an initial value problem. You have the initial value, and you're trying to figure, well, when x go to 45 centimeter, what would be the m? What would be the function, dm by dx? That's the ordered differential equation. Kind of like dy by dx, and it's function of bunch of stuff, huh? And you want to integrate to get the solution. Alright? So we need initial value, and we need now to see how we can get this h, the time step, or the step, that the variable that we are integrating over x. Should we step basically every one, or every, this pipe that's 45 centimeter, should I take it every centimeter, or should I take it every millimeter to get the flow at the end? Alright? So the answer comes from, what's that? Does anyone remember this? Taylor expansion. Exactly. This is Taylor expansion. So Taylor basically say that if you know the value initially of y at function of x, you can find the function at different point x plus h, y of x plus h as basically yx plus hy prime plus h square over 2y double prime plus, you know the drill, right? This y prime of x, the dy by dx, that's what we are after, right? dy by dx, that this formula, if you ignore everything here, you got yourself what? You got yourself a formula for dy by dx, okay? But there's other terms here. You are just saying they are very small. How come they are? Who told you that it's very small? Who said that y double prime is very small? Because it's multiplied by h squared. So that's the whole trick. Okay? That's the whole trick behind this. It's basically assuming h is very small. That make h squared is even smaller. That make h to the power 3 is even tinier. That make h to the power 4, forget about it. Huh? So basically, all those are truncated, and the error we are making is supposed to be small, and that's called, for a good reason, they call it, what do you call that error? If we neglect all this, our formula now has an error. That error is called, no, we truncated the series. It's called, excellent, truncation error. The truncation error is the error that basically you are chopping the Taylor expansion and you are saying, I'm just happy with this. Here is my y prime, or my dy by dx. It's simply yx plus h, minus yx over h. That's it. What about the rest? No, I'm just truncating it. So of course that truncation error will be big if h is big, and will be small if h is small. Alright? And we just want to make it small enough. For example, in the first problem or second problem, when I said within 4s, I want you to make the truncation error small enough that the 4 digits does not really get affected by it. If there's any error, I want it to be basically in the 5th and the 6th digit. Alright? So again, here he basically just chopped this and he called it truncation error, and now here is the formula. Alright? So here is his formula. And so the formula is basically that yx plus h is yx plus h y prime of x. Okay? What is the y prime of x? That's the differential equation we are trying to solve. That's the dy by dx that was given to us. So all you have to do is basically just put dy by dx over here, or that function we are trying to integrate, and you got yourself a way to get yx plus h from yx. From the initial value, you basically can get the next value, yx plus h. Where this is coming from? Again, it's this. Okay, it's this Taylor expansion. It's considering only the first 3 terms, yx plus h and yx and hy prime. Okay, so what we did again, we have this initial value, and now we have a way to calculate this. And graphically, what's happening? What's happening is that he's taking the slope of the function that you are trying to integrate, that you don't know, by the way. If you know it, we are done. Why you are integrating? That function I'm plotting, I don't know it. But that function is the solution for the differential equation. The dy by dx was not the function. The dy by dx was the tangent, was the slope. So I can calculate that slope, because all I have to do is just plug. If this was dy by dx, all I have to do is just put x naught and y naught here. And this y prime now is the slope. So multiplying the slope by h will give me that small part on top of y naught. Right? So really what's happening is that I'm approximating the function that I don't know with that straight line. That's basically tangent at y naught. So now what will happen after that? We got from yn, we managed to get yn plus 1. I will start from here and get the next one. I'm starting from the wrong place. This is not the exact yn plus 1. This is my approximation of yn plus 1. So I will not really end up on that curve here. I will end up even worse. And worse and worse and worse, because specific, not just I'm starting from the wrong x, and I'm not starting, I'm right at the x, but I'm wrong at the y. I'm starting from the wrong y, and also when I calculate the slope, what I'm gonna use in my function? I'm gonna use my xn plus 1 and the y that I have, which is wrong. So I'm starting the wrong point with the wrong slope. Okay? So, I need my pen. So basically, you know, I will start like this, and then like this, and then it will get worse. I will get more and more away from the curve. And we will see this in the example because we will do problem that we know the exact solution. So we can basically put the numerical solution next to the exact solution, and you'll see how you'll keep deviating from it. It gets better if the h is small. It gets worse if h is bigger. Alright? So, Sean, you had a question.
Oh, I was going to say on a solution where it would be kind of like a sine or something.
Yeah, you could get lucky, right? If the solution starts changing the slope, you know, you could basically sometime undershoot, sometime overshoot, sometime you get head on. Right. But in general, let's keep in mind that having a big h will result in more and more deviation, and having small h will basically reduce the error. Right? And so this is the first method we use. This is called the Euler method. Alright? And that's how you're supposed to solve this pipe flow problem. Right? He actually said using Euler method. You will solve it with Euler. So what is Euler method? It's this equation. Yn plus 1 is Yn plus h f of x n and Yn. Okay, let's see an example to understand what's going on. Again, what we are leaving behind is the truncation error, and it's of order of h square. Alright? So that makes this formula basically first order accurate, because if you divide over h, you will basically get first order accurate method. Okay? So Euler method, the formula that we are using right now, like this is not the most accurate, but it's the fastest, it's the easiest. So it will give you a solution like this, but of course the results is really bad. But you compensate for making it very tiny. The h is very tiny. Other methods are more accurate, and therefore it will allow you to have actually bigger h. You can step much quicker with the other methods. Alright? So another error also, this is a graph that I was trying to show you, that basically see the first point and then the second point and third point, you keep basically getting farther and farther away from the actual curve. Right? Another error, so we have truncation error, we explained what is it. Another error is called round off error. So let's imagine someone basically said, I wanna impress Dr. Salam in that homework. I'm gonna make my h, you know, Excel has 1 million cell. I can go 1 million cell. I'm gonna make my h 0.0000000001. Well, maybe the computer doesn't actually keep that many digits, and so when you keep substituting, the number doesn't change. So that's the round off error. That basically by rounding the number, if your solution is within the rounding of the last digit, it may not really show up, right? So you don't want to make it too small so that it will be within the rounding error, and you don't want to be too big that the truncation error in the formula itself is really really big. Yeah. So let's go over this. We'll go back to it in a second. Well, maybe not. All right. So let's look at the second method also. So he basically say, well, in order to reduce that error, you know, we don't want to just basically keep making the error go bigger and bigger, sending us farther away. So he fixed it by basically after getting the first point and before he go to the second point, he basically tell himself, well, I know why this was wrong. This was wrong, or I had this error because I depended on the initial slope. You know, stepping from here to here, the function kind of curves from me, and I kept assuming it's still moving with the initial slope. That's not true. The function changed. It's not. We are not integrating a linear relation. So, is there any chance to fix this point? After I came here, should I basically do something to make it a little bit more accurate? He's not happy with this yn1 based on the initial slope. A better relation should depend on not the initial slope. It should depend on. We cannot get the actual slope, but we can get. So rather than the initial slope, we should get maybe the average of the initial and the final, right? So exactly, kind of basically. So basically, rather than saying let's depend only on the initial slope, I should basically go with the average between the initial and the final. So, but I didn't have the final when I started, but you have it now, or you already, or you have something close to it. I mean, this yn plus 1 is not exactly correct, but it's better than just the initial slope. So what will happen is that after he used the initial value to come up with yn plus 1, he go back again and say, let's do it again, but now with the average slope between this x naught and y naught, or xn and yn, and xn plus 1, and my yn plus 1, and get a better yn plus 1. So when he do this, it's called predictor corrector method. He predict where is yn based on this formula, and then he correct that using the two value. Alright? This of course is more accurate, and they call it enhanced Euler method. So it's Euler but improved slope. Alright? So the formula would basically be two steps. You kind of get y star, that's not the final thing yet, but it's as if you are doing Euler. It's yn plus h, the step you are doing, time the initial slope, substituting dy and dx by xn and yn. Okay? And you get the y star. See how y star is basically yn plus, what's that? That's the initial slope times the h. You know the initial slope is tan theta. So basically that triangle tan theta is this over this. It's the increase in the y over the h. That's why the increase in the y is the h times the slope. Alright, so once he's get his y star and it's not the final thing, he basically go again and say, you know, now if you really want to get yn plus 1, it should be yn plus half h time, and look at this, it's the average or the summation of the slope initially and the slope using that new point, xn plus 1 and yn star, yn plus 1 star. Okay, in the exam what students confuse this thing with is that usually they will do this right, but then when they come here, what do? They say yn plus 1 star plus this. That's wrong, right? Why? Because we are recalculating again based on the initial point. So it's yn. It's not yn plus 1 star. This is basically as if you are going back again. No, let's go back again and calculate yn plus 1 using yn, the initial value. Okay? So the Excel file will basically have at the same xn, you have yn plus 1 star, and next to it on the same line yn plus 1. And that new value yn plus 1, that what go to the next time, or the next x. That's the final, say, what do we have at this xn plus 1. Okay? And so it's basically kind of like calculating the slope twice. The initial slope, right? And the final slope. The initial slope is calculated using xn and yn initially, and the final slope is using xn plus 1 and that yn star, that new point. That's, where is it? It's yn plus k1. Right, every time step. So Euler would be, so if I wanna just do Euler, I will cancel that line. There is no K2. It's just K1. Just the initial slope. H fxn plus 1. Okay, and then yn would be, yn plus 1 would become yn plus K1. That's the Euler. The enhanced Euler is, here is K1, and then let's calculate what's K2. It's the new slope at the end. And yn plus 1 would be yn plus half those guys. Yes?
Once you do the two steps, you get the second yn plus 1. If you want to go again, what would you do next?
You start from, so now, next here, you start from yn plus 1. This yn plus 1 is now your new yn. And you start again from yn plus 1, calculating yn plus 2 star. And you fix it to get yn plus 2, the actual yn plus 2. So every time step, you get the star condition first, the predicted condition, the not so accurate condition, and then you fix it to get the accurate solution. Alright? So every step is basically two y's are calculated. A fake one and the final one. A fake one and the final one. Why do you calculate the fake one? Because it's needed to calculate the second slope. The slope at the end of the interval. Alright? And it goes on and on and on. So, I'll let you read that solution. This is actually a little bit more better than Euler. This is actually second order accurate compared to the Euler, the regular Euler. So now, if you want to improve this even better, this method, what do you do?
You average it amongst 3.
Where are the third one? No, before you average over 3, before you average over 3, what do you do? Think about something else before we average over 3 points. Actually, I did this in my master degree when I had a bunch of ordinary differential equations that I turned them to ordinary, so they were partial, and then I turned them to ordinary differential equation, and then when I was integrating, and I got this, and then before I move to the next time step, or the next x, what should I do?
Would you overshoot it and then average?
No, I would see what happened here is that we calculated this and we were not happy with it because it was based on the initial slope alone, right? So we said, let's use the average, right? And we got this guy. But there was something wrong in this formula. This enhanced Euler is not perfect. Why it's not perfect? Yeah, and so what do you mean by that? What's wrong? I mean, this is correct. That's the slope initially. But is that the slope finally?
No.
Why?
Because you're using the approximation.
Yeah, because I'm using y star. But that's the best I have. Can this be improved? Is there any way I can calculate the slope at the end better? Can I calculate this better? Not yet. Is there any way I can calculate the slope at the end better for a free homework problem? Yes, and Amanda has a free homework problem. So Amanda basically, what did she say? She said, I said, is there any way I can calculate the slope at the end more accurately than this? And she said, can't you use your accurate yn at the end? Yeah, yn plus 1. I can go again that next step, but rather than using yn plus k1, I could use actually, this new value that I had. Not just one time. I can keep doing it forever. I get a better y. I use the slope again and again and again and again. Right? Right. And actually, you could told me, so rather than spending all this time in calculating the slope at the end, you should have... No, we cannot get the exact solution. We are doing all this for a method that doesn't have an exact solution. So, by the way, anytime you have access to the exact solution, of course, go for it. If the method can be integrated analytically, don't go numerical, of course. But no, we cannot have access to the analytical solution. rather than keep fixing the slope at the end, we could spend the time and the computation on shrinking h, right? The reason why we are in this mess is because h was so big, the function kind of curved from us. But if we have used smaller h, the function could really be as if it's lean, it's a line. Any function, no matter how weird it is, over a very small distance, it will look like a straight line. So you need to make h as small as possible to start with, okay? Not small enough to be within round of error, but you will need to make it small so that the truncation error is not really big. All right? And those methods, you will see in the homework, I actually ask you to calculate this using Euler and then repeating it again using, this actually is fourth order accurate. First order accurate, fourth order accurate. And in that homework, and I never told you what's the h in both problem. You have to come up with your own h yourself. And you will realize that, wow, this method, the fourth order accurate, you can make h really big and still you get the exact solution, or very close to, compared to this method. So raising the order of the method basically allow you to have bigger h. But of course, raising the order of the method require you to do more calculation. You know, Euler and enhanced Euler, well, there is one extra line in enhanced Euler. So that's kind of equivalent to shrinking, but it pays off to use higher order, okay? Rather than just cutting the... So he's basically solving problem number 6 now with enhanced Euler. And so here's his two formulas, basically the K1 and K2. And yn plus 1 is yn plus h over 2 and K1 plus K2, right? And so in the homework, I'm asking you to basically step from x equal 1 to x equal 2. And I'm forcing you to use h equal 0.1. So that's 10 steps. So doing it by hand is probably going to take a lot of time. So you may actually find it more useful to put this in Excel. Because once you write the formula, you just have to drag the cell. But in the midterm and the quiz next week, you will have to do it by hand. Alright? So in the exam and the quiz, usually I will tell you, you know, just do 2 steps or 3 steps. I will not make you to go over a very long time. Right? But in the homework, yes, you will have to do it for a long time, and that's why I don't think you should do it by hand. It will take forever to do it by hand. Especially that if I don't tell you the h, and now you have not to do it only once, but you'll do it many times. So it doesn't really pay off at all to do it by hand. Okay? So anyway, so now he's comparing the exact solution with improved Euler and Euler. And you can see how basically the improved Euler, the error is much smaller than, it's order of magnitude smaller. So if it's like the error is 0.2, the error here is 0.02 or 0.01. So it's like 10 times smaller. Alright? Okay. So now so rather than just keep improving the slope at the end, what Chen said was, let's average not just 2, let's average 3. Where is the third would be? Slope at the beginning, slope at the end, slope in the middle, right? Can we get the slope in the middle? Yeah, you bet. We can get the slope as many places as you want. The slope is just dy by dx, the function that you want us to integrate. It's function of x and y. All you have to do is substitute x and y and get the slope of the function. Okay? So this is the Rank-Kutta fourth order method. There is also a 6th order method. We will not talk about it. It's just a bigger formula. But anyway, what he's doing is he will calculate the slope at the beginning, the slope at the end, and the slope in the middle. And the slope in the middle mean x plus h over 2. So we are starting from xn, we are finishing at xn plus 1, and our step is the point 1 we are stepping with. We will get the slope at x You can see here it's x plus h over 2. Alright? And the slope in the middle, he will not get it, or he will not calculate this only once, but he will calculate it twice. Okay? So let's see how this is happening. This case, by the way, is the h times the f, not just the slope. It's the h times the f. So it's kind of, in this graph I'm telling you, the case is basically how much you are, exactly the delta y. It's how much you're adding to yn to get yn plus 1. So if it was just Euler, you would have said yn plus 1 is yn plus just k1. That's what the k is. It's the delta y. It's the h times the slope. It's the h times the tan theta, right? And if it was just enhanced Euler, you would have said yn plus 1 is yn plus half k1 plus k at the end. But because this is the fourth order rank quota, it's k1 plus k4, that's the slope at the beginning, the slope at the end, and twice k2 and twice k3. What's k2 and k3? This is the slope in the middle. And the slope in the middle is carrying more weight than the slope at the two extreme. So it's twice this guy and twice this guy. So basically you have kind of like 6 k's or 6 delta y, and he's dividing over 6. So he's averaging all the delta y coming from different location or different places, predict different y. Alright? So as far as you are concerned, this is the formula that you're going to use to calculate the delta y between yn to yn plus 1. And you would repeat this formula for next step and next step and next step. Right? So the difficulty comes on calculating those correctly. Can you calculate those k's correctly? And the confusion is basically reading this. So again, the formula that I'm substituting in is the dy by dx. Right? So, for example, here the dy by dx is this. 1 minus 1 over xy. This is my slope. This is the function of x and y that I want to evaluate initially, finally, and in the middle. In order to evaluate this function, or find its value, what do I need? I need the x and the y. I need to plug the x and the y in it and figure out what is this number. Is it 0.1, 0.5, 0.73? What is the x and y that I'm using? For k1, it's xn and yn, the initial value. At the end, it's xn plus h, of course, because it's at the end. And yn plus k3. What's k3? It's what's calculated in the middle. In the middle, it's always xn plus h over 2. xn plus h over 2. Okay? Because it's the middle. And what is the y? It's different. Here it's yn plus half k1 that you just calculated. Here it's yn plus half k2. And here it's yn plus half plus the whole k3. So basically it's as if he's calculating the initial slope, and then he say let's calculate in the middle based on the initial slope, and let's calculate it again in the middle using the new improvement in the slope, and let's calculate it at the end with the last thing that I had, and let's average all of them. Alright? Is that clear? Alright, so it's basically the trick is to practice it right when you are doing this calculation. Alright, so for example, here is here we can see this. So here's the function he's integrating. F x and y is x plus y. Alright, or this is as if so this is as if basically saying dy by dx is x plus y. Okay, that's a function we want to integrate, and he's giving us the initial value at x naught equals 0, y naught equals 0, and we want to integrate this with and get a fourth order method, or the formula that basically say yn plus 1 is 1 over 6, sorry, it's yn plus 1 over 6 k1 plus 2 k2 plus, you know, the so how I'm going to do this? I will make one big table like this, and I'll start with xn and yn, and then k1, k2, k3, k4. Alright? What's my x's? What's the first x and first y I should use? 0 and 0. Right? And he said the h is, say how much is the h? 0.2. So that make x1, if x1 is 0, x2 would be, what's next x? 0.2 and then 0.4 and then 0.6, and we keep going until we hit the final result that he wants. Right? So how much is the k1? You can just go back to the formula and read that k1 is f h multiplied by f of xn and yn. That's the easiest one. That's the initial slope. Right? So what is h? 0.2. And what's f of xn and yn? That's simply x plus y. So whatever the function, whatever this thing is, x plus y, x minus y, x sine y, you just plug the x naught and y naught. In this case, it's 0 plus 0. So that's 0. Right? So, you know, it's basically 0. K1 is 0. And then what? You calculate K2. What's K2? H f of x of x plus h over 2, right?
Well, yeah, x and yeah, h over 2.
And yn plus k1 over 2. And you know why it's h plus 2 and k1 over 2? Because you want to get it in the middle. What is the slope in the middle? Right? So you basically just substitute what's the h, it's 0.2. What is the function now of xn plus h over 2? That's 0 plus 0.1. That's 0.1 plus y n plus k1 over 2.
Y is 0, k is 0.
Right? So I'm just substituting. I don't even care what is it. I just substitute and get the number. Right? So that make it 0.1 plus 0 multiplied by 0.2, that's 0.02. Now we are getting something. Now the slope will start moving and we will get, because if it's all 0, we will never leave that point, right? We'll just mean 0 forever. And then K3, and it will be again the same x plus or yn plus K2 over 2. Now you will have that K2 over 2, and you will get K3. So for K3, we will get 0.2 and the same 0.1 plus 0.01. That's K2 over 2. All right? And so how much is that? 0.02, 0.03? 0.022? Why? 0.1 times 0.2, that's 0.02, and then you have 0.01 here. 0.03, right? Yeah, it should be 0.03. And then K4 finally is h times the whole x, xn plus h, and K3, the whole K3. Not K3 over 2, the whole K3. So I'm just repeating those formulas. Okay? I'm just substituting with those formulas. That's it. So I will get not just 0.1, I'll get 0.2 now. This will be 0.2 plus the whole K3, 0.03. And then I multiply the whole thing by 0.2. And you get this number, and then you basically average 1 over 6, all these things. Okay? So this is the difficulty of this method, that you have to remember those formulas, okay, or you have to be accurate in using them, and you can see, you have to, so the students basically don't see the h over 2, they just think it's h, they don't see it's k3, not, they assume it's always half because they have been using it for the next 2 steps. All right. All right. So once, so it could help if you just write the formula for yourself too. Okay. And look at this. He actually have the exact solution. All right. And this is the error time 10 to the power 6, meaning that the error actually is this divided by 10 to the power 6. That's how accurate the rank-Kutta method is. All right. So it's really accurate, that it allows you to really step very, very quickly through the solution. So now he's comparing the same equation with the same h but different method. And you can see Euler, this is the error of order h, this is enhanced Euler of order h squared, and that's rank-Kutta. Of course, the saving comes from the fact that you're calculating the slope 4 times. All right? So there is no magic. It's basically, right? And that's the exact solution he got it by integrating analytically. Right? And the other rank-Kutta method, which is even 6th order, will basically will be even more better. But we will just stick to those guys. Right? Questions so far? 3 formulas, just substitute in them. The only trick about the homework, let's go back to the homework for a second. So this is rank-Kutta using this formula. It's basically just like this. Okay? Now here, what's weird about this problem? Huh? Of course, because that's dy by dx. So dy by dx could be function of y. That's okay. dy by dx is function of y. Now what else is weird about this thing? F, d, and gamma, this are all constant, and they are given here for us. What's weird? That's nice. First order ordinary differential equation. So it follows what we have been solving right now. It's first order. That's okay. What's weird is that we don't see x. There is no x. So when you are doing it with Euler, and then you are doing this with rank-Kutta. So when you are doing it with rank-Kutta, and you are supposed to do it at x and then x plus h over 2 and x plus h, where is the x that you are substituting in? There is no x. So the slope doesn't change. You still are doing k1 and k2 and k3 and k4, but with the right correct y. Initially yn, k1, and when you do k2 it's yn plus k1 over 2, and then when you do k3 it's yn plus k2 over 3, and then when you do k4 it's yn plus k3, the whole k3, but it doesn't matter what's the x. There is no x. Okay? And what's the formula for something like this? This would be just like when I say yn plus 1 is yn plus h times the f. This is m. N plus 1 is f of n plus the h multiplied by that function. It's supposed to be function of x and m, but unfortunately fortunately actually, it's just function of m. I mean, that saves us one variable. We don't have to worry about it. But generally speaking, the dm by dx or the dy by dx we are integrating, it should be function of x and m, not just m. All right? What's also not really nice is that we don't have the h. You are supposed to come up with the h yourself. The h that will make the solution is kind of mesh size independent or step size independent, You want to make the h small enough that, see, now I'm changing the h and making it smaller, and I still get the same answer. That's when you say that solution doesn't depend on my step size. So all those numerical simulation, when they simulate flow over airplanes and the flow in the room, and they also use a step size in space, x and y. And the first question they always ask the students, when they are defending their thesis on, when you are seeing a presentation in a conference, something, the first thing that comes to your mind, were your mesh small enough to achieve that? To achieve what? That the solution does not depend on the step size, or in this case, if it's in 2D, the mesh size. You want to make the, so you always ask them, did you check the solution is, when I was a student, they asked me that too in my defense. When I'm doing my master's degree, they said, well, your solution was mesh independent? Are you sure that the step size was small enough that if someone came after you and make it even smaller, he will come up with the same answer? Right? Huh?
And your answer was?
Yeah, I said I made it as small as possible. It cannot get any smaller than this. It's like, so this is important, right? And you will figure out this yourself. So obviously you cannot do this by hand. You have to do it over Excel. And so does anyone have question doing this over Excel? You know how to do that? It's basically filling that table with Excel. So rather than you have to write those formulas, basically you basically say it's h, you will have h somewhere, and you bring that, or you refer to that h, time, and you bring the x from the next step, or from the next cell. Okay? If you have difficulty, let me know, and then maybe I can help. Maybe I can give you K1. I make you a spreadsheet with K1, and then you have to come up with, or I can give you K1 and K2, and then ask you to fill K3 and K4. If I hear enough complaints, I will. Amanda had a question. So x is not in the formulas, right? But of course, it's in this y-axis. I mean, it's basically in the first column, because eventually what we are doing, we are getting y for that x, and again we're getting another y for that x. Yes, the calculation does not depend on the x, but we have to do it for different x's. Say that again. So the solution depends on the h. Notice that all those k's, they have h in them. So of course, the h that we are using, whether we're going to step every 1 centimeter or 1 millimeter or 5 centimeter, it will make those keys different, and it will make the solution deteriorate or improve, depending on whether h is small or not. Okay? It's just what's weird is that the slope itself does not depend on the x. All right? Good. So now let's see what happens if, more serious problem now. Method for systems. So you have two equations together, or differential equation, or if you have a second order, what do you do about it? All right? So first, system of ordained differential equation. To have a system, they have to be coupled. It's not like dy1 by dx equal 5y1, and then dy2 by dx is 5y2, and those are not coupled. You solve each one of them alone. But if the y1 and y2 is basically intermingled between the two of them, you have to solve them as a bunch together. Okay? And the second order is basically when, rather than having y prime, you actually have the second order or the third order or whatever. Right? And it turned out that if you have a higher order, ordained differential equation, third, seventh, whatever, you will turn it into, with a small trick, you will turn it into basically a system of first order differential equation. So if you have a second order, one second order ordained differential equation, you can turn into two first order differential equation. If you have third order ordained differential equation, you can turn into three. All of them are first order. If If you have seventh order, you turn them into 7. Every one of them is first order. We'll see how this is being done. Alright? So for example, this is one of the equation that you will get in solving boundary layer. You will do this in 4273. You will know how to come up with that equation, that ordained differential equation. But let's assume we have that ordained differential equation right now, and we are solving it for those boundary conditions. You get f of 0, f prime of 0, and f second prime of 0. Why? Because it's third order. Not only it's third order, but it's also what's evil about this equation. This is another way to write it, by the way. So rather than saying, what is that variable? That's eta. That's the independent variable. Rather than m of x, you know you have f of eta. That's okay, right? Excellent. That's what's evil. Robert is right. What's evil about it is that it's nonlinear. The f is multiplied by f double prime. Solving this equation will give you the velocity profile inside the boundary layer. That's important because that basically tells you the drag in the airplane or anything, any flat plate moving. That basically solving that slope will tell you how much drag force that the engine need to overcome so that this thing can keep going. Alright? So again, solving this is basically by turning it into 3 first order differential equation. Alright? So how is that being done? Can you stop playing with so seriously, stop. So how do you turn this into 3 first order differential equation? Well, you basically say, I don't like y triple prime. I wish this was y prime. Only y prime. Yes, it is y prime. It's the second derivative prime. Alright? So you can actually define the second order to be a new variable. Let's call it y3. It's a new variable. It's called y3. Then this equation become y3 prime. We turn it into first order. And what about this y double prime? That's actually y3. And what about this y? Well, that's a new thing. Let's call it y1. Alright, so you define basically y1 as y and y2 as y prime and y3 as, and so by this trick basically rather than having one third order you have 3 equation, all of them are first order. Okay, now let's look at this one for example. So that's second order, y double prime plus 2y prime plus 0.75 y equals 0, and because it's second order you need y of 0 and y prime of 0. You need the 2 initial condition on it. Okay? And so he basically said, let's make y equal y1 and y2 is y prime. So this equation doesn't have being a second order in y, it become first order in y2. Right? Y double prime become y2 prime. Why? Because we just said that y prime is called y2. So this become y2 prime, this become y2, and this y is y1. And what's y1? So y1 is basically dy by dx. So y2 become y1 prime. So now this become those 2 equations. This is by substitution, just by saying let's get the highest order y double prime and call it something prime. I will call it y2 prime. And then the y is now y1, and by definition, since y prime is dy by dx, y prime is y2, then y2 is basically y1 prime. Right? So now if you have those 2 equations, and look at the boundary condition. The boundary condition were for actually y and y prime. Now the boundary condition is for y1 and y2. So this is basically a system of ordinary first order differential equation. 2 of them, 5 of them, 7 of them, it doesn't matter. So if you have this, you will turn it with this. And now let's ask ourselves, how do we integrate this? How do we solve this? Bunch of ordinary first order ordinary differential equation that you have to solve them simultaneously. How do you solve those guys together? Let's solve them with the easiest way ever, Euler. And then worry about enhanced Euler and Rank-Kutter later on. So although the homework doesn't have a system of ordinary differential equation, the quiz next week may have a system of ordinary differential equation. Okay, so solving them, let's solve these two guys with Euler. Here's y2 prime and here's y1 prime. So y2 prime is minus 2 y2 minus 0.75 y1, and the other one y1 prime is just y2. We can actually say it's not just equal, it's by definition, but assuming we are just solving two ordinary differential equation, that we don't know where did they come from. They just threw two equations for us and solved simultaneous equation. Again, because see how y1 and y2 show up in both of them with those two initial conditions. y1 of 0 is 3 and y2 of 0 is minus 2.5. How can I solve this using Euler? The easiest thing ever. xn, right? What's my xn? Initially it's 0. Okay? xn is 0. And what should I write here? We used to write yn, right? What should I write instead of yn? y1 of n and y2 of n, right? The number of variables we are solving as function of x. What's the initial y1 of 0? That's 3, and this guy minus 2.5. And what was the formula for Euler again? yn plus 1 was yn plus h x of n and but this time comma y2 n. The function I am integrating is not just function of x, it could be function of x, y, 1 and y2, and y3 and y4 and y5 and whatever that function is. Right? Correct? And, well, this time, just like our homework, the function actually is not really function of x. You should expect, normally, this also should be function of x, but we don't have x. That's okay. We'll just calculate the slope anyway. And so here, basically, I will just calculate this, the h multiplied by f of, so this will be, say, f1. And this will be y1 and y1. And you have another formula like this for y2. So each one of them has its own slope coming from its own equation. Right? So there is y2 of n plus 1 equal y2 of n plus h times the slope f2 of xn, y1 of n, and y2 of n. Can you guys see this? Alright? So let's calculate the first slope, x, y, 1, and y2. So for the first equation for y, to get y1, we need the slope of 1. So it will be the h. What's the h we are studying for? Let's assume we want to step with 0.1. So in the homework and in the exams, I will give you the slope. I will not let you try and error on it. There's not time for it. So let's assume the h is 0.1. So we are basically getting the solution every 0.1, 0.2, 0.3. So this h will be 0.1 multiplied by what? This is the slope of y1. I go to its equation. It happened to be just y2, right? So y2 of n, right? It's the original, this is Euler, so I'm just using the original or the initial slope, right? So it should be this guy, minus 0.25, sorry, minus 2. Because that was the initial value. And so y1n plus 1, this guy should be basically the 3 plus this. That will give me the new y1. And how about y2? What is y2? It will be h multiplied by the f2 of x and y1n and y2n. So how much is it? The h is 0.1 multiplied by the slope of 2. I go here. And it's minus 2 times y2. Minus 2.5 minus 0.75 multiplied by y1, which is 3. That's hf2. And so the new y2 is this initial value plus whatever I calculated from here. Has this been Euler, enhanced Euler? We will not be happy with this new y's. Those will just become the y1 star and the y2 star. And we will go again, one more column, one more calculation to calculate the actual y1 and y2 at n plus 1. Has this been Rank-Kutta fourth order method? We will actually have not just hf1, we will have 4 of them. Kind of k1, k2, k3, k4. And all those k are not just function of y1 and x, they are function of y1 and x and y2, depending on the equation. Okay, could have as many variables as it takes. You have a system of differential equation, and each one of them could actually involve the other guys, or some of them, or right. So this is again the formula that we just plotted right now. Okay, so I see how y1 is calculated from f1, from the slope of its equation. And y2 is calculated from f2. Each equation gives you the slope of one variable. Okay? And so here are the equation. This one just simply y2, and the other one is the equation for it. And he keep repeating this, you know, over and over. But what I'm trying to say over here is one equation is giving us y1, and the other one is basically giving us y2. Right? And you can see the solution as it's basically marsh. y1 of n and y2 of n. All right? And this would be almost the same, except that you will actually have 4 slope every time step. And the slope will depend on those variables. Question about this? Maybe the next homework we will have a system of ordered differential equation. Right. So you look at this one. Let's finish by this one. I have 1 minute. So y double prime equal xy. Second order. I don't like it. I need only first order. What do? Change y prime to call it something else. So he called y prime as basically say y2. So this equation become y2 prime equal x times y1. And what's y1? We just call it y prime to be y1. So then by definition, y1 prime is basically y2. And that's how you end up with the 2 equations. All right? And you integrate them, and we'll do this next time. Thank you.